So let's look at some of these names. What do you get for the first one?
It's like 2 chloros, 3 propyl.
Close. I would go with 2 chloro, 3 methyl hexane. Yeah? Right. Because the longest chain here is 1, 2, 3, 4, 5, 6. So even though it looks like the chain should go across the middle, we have to go with the longest continuous chain, which actually goes down. All right, this one, the next to it, this proposes a little bit of a problem. What's the problem with this one here? It supposes a bit of a problem.
HO.
Yeah, what is that? What that is? It's called an alcohol, and we'll talk about it in the next chapter if we get there. But this is a little bit different than what we've done so far. We've dealt with chlorine and bromine. We haven't dealt with alcohol because that's what we call a functional group. The chlorine and bromine are kind of two, but they're named the same. But the alcohol really completely changes how a molecule like that reacts. So if it has an OH on it, it's going to do totally different things. It's going to behave in different ways. And so that becomes more important than just another thing that's stuck onto it. So we actually name that at the end. And if we have time, we'll get to this in the last chapter. We might not even get there this semester. But so this one would be named, I'm just going to give you the name, and then we can kind of take apart where that came from. This one would be 3 chromo 4 chloro cyclopentanol. And let me show you where that name comes from. Because of the special significance of the OH, which we call the alcohol, that actually changes the end of the name. So instead of cyclopentane, it becomes cyclopent and all. When we see that OH, we put the all at the end. Also, because that one's so important, the number 1 carbon when we're numbering around the ring always has to start right there because of that important piece. So we don't get to put the 1 over by the Cl or the Br, which would actually be better for our numbers, but we put it here. So we'd go 1, 2, 3, 4, 5. That's where that name comes from. Don't worry about that too much. We're probably not going to get to that this semester, but that is how it works. All right, let's look at these next couple. What do we have here? What do you name this one? Right, 3,4 dimethyl hexane. Let's jump down here.
Yeah, 7 until 9.
Remember, we need to number the longest possible chain from wherever it gives the lowest number for the substituents. So I would say we'd do this the other number it the other way and call it 3-methyl bromine. So our longest chain is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9.
And if you start from the beginning, 1, 2,
Mhm.
3.
Then it would be 7-methyl, right? But that number is higher. We always want the lowest possible numbers for the substituents. So the 3-methyl is better than 7-methyl. All right, a couple more to go. Let's do this one. Yeah, this would just be methyl cyclopropane. We could say 1-methyl, that's fine, but we don't really need the 1 there because there's only one thing. So you could put it there or not. Because if it was 2-methyl cyclopropane or 3-methyl cyclopropane, it would be the same thing. All right, and then finally this last one again with the alcohol, we have to count around the ring, figure out how many carbons we have. I think I wrote down the same number as up there. This is like a stop sign, so that's an octagon. 8 carbons. So we would call this one cyclooctanol.
Why we not take the first one?
Where?
Yeah.
Here?
Yeah.
Why do we not do what?
Why we not start off?
From somewhere else?
Yeah.
Because where this one comes off of, we want to make that 1, just like we did over here.
Okay, we have 2.
That's the same thing. So it would still be the same molecule. So we always want to start numbering at one of the substituents if we can. All right, good. Let's go the other way then. There's one up there already, 2,2,3 trimethylbutane. Let's see if everybody else can get a name up there, and then we could draw the structures from the names. So something different from what you drew before. Let's post a name and try to draw the structures from that. And we got, that's 6. Almost everybody got a structure up there. Let's see if everybody can get a name up there. It might help to draw a structure first, then name it, put the name on it, but that's up to you. Thanks. All right, we got 3 names up here. Let's get a couple more. Thanks. Should that be ethyl? Yeah. All right, just 4? All right. Did you get structures for them? Video structures? Okay, let's look at what these might look like. So 2,2,3-trimethylbutane, I would draw like this. First, you're going to draw that butane. And then methyl groups at 2 of them, and 3.
Can we draw like one line from upper to lower?
Yeah, but it looks a little better if you do it this way. This is more traditional, but that's okay. All right, then we've got 1-chloro, 2-ethyl, 4-fluorocyclohexane. Again, we're going to start at the end of the word, so we get the main structure first, which is the cyclohexane. There's cyclohexane. Then I would, since we got a lot of stuff at different numbers, we could just number this. It doesn't matter where we start because there's nothing on there yet. You could start anywhere and go any direction, doesn't matter. But now we know 1 should be chloro, 2 should be ethyl, and 4 should be fluoro. Okay. 4-bromo-5-methyl-octane. We're going to draw that octane first, so 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. We want a bromine at 4 and a methyl at 5. So that's 4, and this one is at 5.
And can we draw like octane?
No, because that's cyclooctane.
Like circle, can we draw like this?
No, because that's cyclooctane. That's a different molecule that has fewer hydrogens on it. So you got to watch for that right here, this word. Tells you that it's in a ring. If it doesn't have that word, then you draw it straight. And the last one, 5-ethylpropane. There's propane.
It's 3.
I was just copying what's on the board. I'm not sure where the 5 comes from. Because there's not 5 there. Yeah, so I'm not sure where we go with that. So we got our propane, we put our ethyl somewhere. Actually, there can't be any ethyl propanes because even if we had something like, let's say, 2-ethyl propane, would be like this. But that's actually 2-methylbutane is the better name for that. Because you can have 1, 2, 3, 4 carbons, and then the methyl comes off number 2. All right. All right, let's move on a little bit here. I want to talk about 2 categories of organic molecules, our hydrocarbons, and then we'll get into the alkenes, the double bonds. But what we want to look at is saturated versus unsaturated hydrocarbons. These are terms that are often used to describe the structure. You may have heard them in things like saturated fats and unsaturated fats, which is the same, actually the same thing, or applies to the same thing. A saturated hydrocarbon is one where the carbon has the most possible hydrogens attached to it. So if we take something like butane, 4 carbons, I'm going to draw the whole thing out as we did before. We call that a saturated hydrocarbon because there's no way you can put any more hydrogens in there. 4 carbons can have 10 hydrogens with them in a molecule. Can't fit any more than that. So that's C4H10. Can't fit any more than that. Let's compare that to cyclobutane, which is where it's in a ring. Are butane and cyclobutane isomers? They're not. Why are they not isomers?
They don't have the same formula.
Right, they don't have the same formula. Cyclobutane is C4H8. So that would be unsaturated because it has fewer than 10 hydrogens there. Now, it's easy if you see something like a hydrocarbon that's just in a straight line, that's obviously saturated. But even something like this, which is an isomer of butane, if we have 4 carbons that are arranged like that, not cyclo, and we add in the hydrogens, this molecule is called 2-methylpropane. It's an isomer of butane, so it's sometimes called isobutane. That's just a common name. Its formula is also C4H12, so that makes it saturated. So saturated hydrocarbons have the formula CnH2n plus 2. We talked about that a little bit before. However many carbons there are, you're going to have double the number of hydrogens and then 2 more. And that's saturated. That's the most that can possibly be there. The other way to make unsaturated hydrocarbons is through multiple bonds. That's what we're going to get into next. So if we had something like this, we have butane, but we put a double bond in there, like that. Now we can't fit as many hydrogens in anymore because each carbon, again, needs 4 bonds. And if we count that up, that's called 1-butene. We'll get into that naming in a minute. But if we count that up, that's also C4H8, which makes it unsaturated. Right. And we can say in general, unsaturated hydrocarbons will have something like ring structures or multiple bonds. That's what gives it that unsaturation. Those electrons are used for something other than bonding to hydrogen, so those are unsaturated. Make sense? So we should be able to look at a formula and know if something is saturated or unsaturated, and also to look at a structure, looking for those double bonds and those rings to know if it's saturated and unsaturated. When we talk about fats, saturated versus unsaturated fats, we're dealing with multiple bonds. Saturated fats have long carbon chains of single bonds, so they can pack together very well, have strong dispersion forces, and that's why they're usually solid, like butter or animal fats. And unsaturated fats have double bonds in them that cause them to bend, and that makes them usually liquids like olive oils and things like that. If you hear about things like omega-3 fats, those tell you where the double bond is. Omega means the end, so omega-3 means 3 carbons from the end, there's a double bond. And those particular fats are used in biological processes, and that's why they're important. So that comes down to this type of structure. A monounsaturated fat would have 1 double bond, a polyunsaturated fat would have multiple double bonds. Okay, that said, let's look at some alkenes. Alkenes are double bonds between carbon, so stuff like that. It's a little bit tricky when we talk about it because it only differs by 1 letter. That little E there instead of an A means that there's a double bond involved. So we've got, let's see some examples here. Where I was going. With naming, it's pretty easy. We name them like a functional group, like that alcohol we talked about. So instead of putting something at the beginning, we put something at the end. And the way we name an alkene is by changing the A in alkanes to the E in alkenes. So let me show you an example. Ethane looks like this. If we put a double bond there, we get ethene. All right. So one thing you also notice, I drew the shape a little bit differently. Let's look at the shape that a double bond puts in that molecule. I can pull up this thing again. All right, so I'm going to draw a double bond between 2 carbons, and that gives me this nice picture. So very different from that single bond, we now have a totally flat structure. See that? That double bond causes it to be totally flat because of how the electrons are being shared in that bond. This is something you'll get into if you take more chemistry, but we'll just say the electrons are shared in this specific way. I wonder if I can get both of those on here. Oh yeah, there they are. Okay. So on the left, I've got the ethane, and on the right, ethene. So you can see the different shapes in those structures. That ethene, the double bond, is called trigonal pyramidal shape. Flat, 90 degrees, or 120 degrees. Whereas we know that this angle is about 109 degrees. So a little bit wider apart. Makes sense because there's fewer things connected there. So to name alkenes, again, we're going to do the same thing. We're just going to change it from ane to ene. But there are a couple little differences that we have to keep in mind. So let's look at some examples. First off, there can be different alkenes that are not actually the same. So these two molecules, for instance, are both 4 carbons. Everybody see the 4 carbons? So that would be butane. And then it's a double bond, so that makes it butene. But these are different molecules. In the first one, the alkene is at the end, and the second one, the alkene is at the middle. So we have to reflect that in the name. We can't call them both butene. So what we do is we use a number to show where that double bond starts, and that's how we make the distinction. So we call this first one 1-butene, and we call the second one 2-butene. And that's how we distinguish those two different butenes. We're going to look at another one. I don't know if we'll get there today. Another way to distinguish them as well. All right, another example. Here's now hexane, but that double bond can be in 2 different places. Like other functional groups, we want to number the chain so that the double bond has the lowest possible number, because it's this important functional group. So when we number that first structure, we want to start on the right. Go 1, 2, 3, 4, 5, 6. The bottom one, it doesn't matter because we're going to get the same number either way. So the top one is 1-hexene. The bottom one is 3-hexene. So let's make a couple notes about this. Double bond gets lowest possible number. All right. Okay, the other thing that comes up sometimes with these double bonds is that the double bonds have to be a part of the main chain if possible. So this doesn't happen all the time, but let's say you have a structure that looks like this, with this double bond coming off of the 3rd carbon. Part of this gets solved by the fact that you can't really name that as a substituent. So based on our old rules, we'd want to say, okay, that's a 5-carbon chain with a methyl group coming off. But because it's a double bond, it's not really a methyl group. It's different, it's CH2. So the solution to that is we put the double bond inside the chain. And even though it's a little bit shorter, we call this our main parent chain. And we number it 1, 2, 3, 4. And then we call the other part the substituent, the ethyl substituent. So this becomes 2-ethyl 1-butene. There. The double bond should be a part of the main chain. So it should be part of the main chain and should have the lowest possible number. All right, let's try some. I'm going to draw some structures with some double bonds in them, and you come up with the names. Give these 3 a try. So you got some good names. You got another minute or so to think about it. All right, so for this first one I got, again, we're going to kind of step through this carefully, but we want to find that main name first and then figure out where the substituents are. In this case, the main one is cyclohexane, but because of the double bond, it's really cyclohexene. So we can start with that. And then we need to number to figure out where the substituents are. And we want to start at the double bond, at either carbon. In this case, maybe we start here so that the chlorine gets the lower number. 1, 2, 3, 4, 5, 6. Both sides of the double bond, if we're going to start at 1, the other side of the double bond has to be 2. So we can't go back the other way. We have to go along the double bond from 1 to 2. So that tells us that our substituents are at 4 and 5, 4 chloro, 5 methyl cyclohexene. If you did 4 methyl, 5 chloro, that's okay for our purposes. If you go on, you'll learn more specific rules about that.
And do we need to name this double bond or not?
Not number it specifically because it's at 1. You could put a 1 in there also if you wanted to. You could say 1 cyclohexene. But just having that E in the name here, that tells us the double bond is there.
So we cannot start with the CO.
Right. You have to start on the double bond. That gets a higher priority. It's more important. All right. For this one, this is another one that gets a little tricky with the chain that we have to pick because we need that double bond. So we can't say that the 6-carbon chain straight across is the main chain because that doesn't include the double bond. We have to use this one like that. And then again, we want to start numbering so that the double bond has the lowest possible number. So that would be 1, 2, 3, 4, 5, 6. So we've got a double bond that starts at 2, goes between 2 and 3. And then we've got an ethyl substituent coming off of carbon number 3. So this name should be 3 ethyl 2 hexene. We need that 2 to tell us that the double bond starts on the 2nd carbon. All right. And then finally, the only tricky thing about this one is that we need to make sure to give that priority to the double bond. So normally we would start counting from left to right because then the 2 methyl substituents would be on number 2, but we can't do that because of the double bond. So we have to start and go from right to left, count it like this: 1, 2, 3, 4, 5, 6. Yeah. So that means that this number, or this name would be 5, 5 dimethyl. And we could just say hexene, or we could say 1 hexene with an E to show us that there's a double bond there. All right. So you think you can do that? Maybe put it together. There's going to be one more bit that we look at with these, but I don't want to get into it right now because we're too close to the end. We'll get into that on Thursday and talk about triple bonds and get into the next chapter a little bit probably. And we'll have a quiz on Tuesday. So 2 labs tomorrow.
All this
It's
of
Tuesday.
name, yeah?
Yeah, all the stuff from this chapter, the names and the structures and things like that. We'll also learn some reactions on Thursday. That is, this thing can be turned into this thing in this way. So that will be there too. All right. All right, thanks. I'll see you tomorrow. I think we made it through the whole semester without risking wearing too warm of clothes for lab because it's going to be cold again tomorrow. So, yeah.